Hello and welcome back to another exciting episode of Physics Notes with Mr. Wellsby. Today we're going to be talking about Newton's second law. So we've done the first and the third. So just a quick review of what the second law is. The second law is as follows. Acceleration is proportional to force. We often see this written as just F is proportional to A, but really as a formula, the way that you're most commonly going to see it is just this. This equation is often referred to as Newton's second law. Now, if we want to be a bit more specific, what we can say more accurately, is that the net force is equal to the mass times the net acceleration. So for example, if that means there is a upward force of 5 and a downward force of 3, the net force would be 2, and that means we could calculate the net acceleration based on the mass. It is important to note that force is a vector. So we need to take into consideration the direction or positive and negative. So positive or negative has direction. We're thinking about it in those terms. Okay, so let's take a look at this first problem here. And in fact, why don't you give these 3 problems a try? You can hit pause on the video, try these 3 videos, and see how you do. All right, so hopefully you've had a chance to pause and try these out for yourself, and let's give these a go. So we have a 5 kilogram block being pushed to the right, so there's an applied force, we're going to call this FA, and it's along a frictionless track, so there's no force opposing it, and this force is equal to 10 newtons. What is its acceleration going to be? Well, let's take a look at what we know. So the mass is 5 kilograms, the force is 10 newtons, and we're trying to solve the equation F equals ma to solve for the acceleration. And in this case here, if we rearrange the equation, we have A equals F over m equals 10 over 5 equals 2, and the unit that we use for acceleration is meters per second squared. So if you have a 5 kilogram object, you apply 10 kilogram force, and the acceleration on that object will be 2 meters per second. Now for the second problem, we have a 650 kilogram car accelerating 4 meters per second squared south. What is the net force acting on it? Well, I'm not going to bother drawing a picture for these next 2, but this is what we have. We have F equals, that's our question mark, m is 650 kilograms, and A equals 4 meters per second squared. So plugging it into our equation, we have 650 times 4, which is going to be 2,600 newtons. And lastly, 1,500 kilogram ice cream truck accelerates from rest to a speed of 45 kilometers per hour in 8 seconds. Well, the first thing we need to do is convert this. So 45 kilometers per hour divided by 3.6 gives us a value of, just one moment, 45 divided by 3.6, 12.5. So this is 12.5 meters per second, and it's from rest, so we've got that extra bit of information there. So let's see what we know. We know that V naught is equal to 0. We know that V equals 12.5. We know that T equals 8.0 seconds. And so we're trying to find, so this is what we've been given, and we also know that the mass is equal to 1,500 kilograms. And so let's take a look and see what formula is going to make sense in this case. Well, in order to find the net force, we need the following equation. F equals m times a. Now we don't have F, and we also don't have A, but based on the information that we do have, we should be able to find that. And so let's take a little detour and try and solve this one here. So A is the change in velocity divided by time. In this case here, the change in velocity is going to be, the change in velocity is going to be 12.5 minus 0. This is going to be 12.5 divided by 8, and that gives us a value of 1.5625 meters per second squared. And if we multiply that acceleration by our mass, then we have a total of 2,344 newtons, and that would be our final answer there. Equals 1,500 times 1.56 equals approximately 2,300 newtons. Okay, so we've got the basic ideas here, how to use the formula. The next important topic for us to make sure that we have a good grasp of is the idea of free body diagrams. Now, free body diagrams are the picture portion of trying to solve using the disk method. So for a free body diagram, every force should have a labeled arrow. So we can just make it simple. We represent the object in question as a box. We draw all the arrows that we can, all the forces that we can think of as arrows. The direction of the arrows does matter. They're representing vectors. So essentially the size represents the magnitude and the direction represents the direction, obviously. And we should start in the center and move outwards. So I'm going to do the first few examples, and then please pause the video and try the rest of them out for yourself. So the first example here is we've got frictionless ice. It's got an icy surface here. There's a puck that you'll see I'm drawing as just a rectangle or a box, and we're thinking about all the forces. So in this case here, you can think of the force of gravity. That's going to be one force acting on it. But if this was the only force, then it would be moving downward. So we know there must be some sort of force to cancel that out. Because if we only had an unbalanced force, if we think back to Newton's first law, anytime there's an unbalanced force, there is an acceleration. We know this is not accelerating downward, so we know that there must be some other force to counteract that, and that force is the normal force. Now you'll notice that I've drawn these two forces. To the best of my ability, I've drawn these of equal size. And one way that we can indicate the vectors are equal size is just by drawing a line across it that way. So this puck is sliding along frictionless ice, which means that there's no friction acting against it. So let's assume for a moment that this is moving, and we can see these direction lines, it's moving off to the right. One common misconception is that there must be some sort of force for an object to continue moving. But in this case here, because the ice is frictionless, we know that there is no friction or no force pushing this puck to the left. And so if it's not accelerating, which we can assume here it's not, it just says it's sliding along, it doesn't say it's slowing down or speeding up. So that must mean that there's no net force in the x direction either. So we've already discussed how there's no force in the y direction, the up and down direction. We also know that there's no force going to the left or right, or no net force going to the left or right. So in fact, this, even though the object is moving, this is a completed free body diagram. So there's two forces up and down that cancel out perfectly, and there's no forces left or right. Now, if there was, this is not correct, but if there was some friction, we would see an object moving like this. We would see it would be slowing down as it progressed. Okay, let's try out the second one here. A dragster accelerates from rest. So I'm just going to draw my dragster as a box. You don't need to get fancy with it. And we know, again, we have the two forces that we mentioned in the last one. And as long as it's not in space, we're always going to be able to reliably say that there is a force of gravity. And if it's not accelerating up or down, it has to be balanced by a normal force. Now, in this case here, it's accelerating from rest, which means that there is some force that's causing it to accelerate. And it must be an unbalanced force if it's accelerating. So there is a force to the right. We're going to call this FA for the applied force. And We don't necessarily know, it doesn't say here if there is friction or if there's not friction, but we do know one thing. We know that it's accelerating to the right. And so if it's accelerating to the right, even if there is a friction force, we know it's going to be smaller than the applied force. So this one here would be optional. There may be friction, there may not be, but if there is, we need to make sure that our applied force, this force to the right, is going to be the bigger of those two. But we don't really need to include that based on the question. There's nothing to indicate there that friction's playing a role. Okay, what about this one here? Now this is a bit more confusing. We're not going to cover this in too much detail in terms of it being on a test, but we will do a lab-based practical on this later in the year that talks about basically how do we solve forces on an inclined plane. So this is going to be the last one I try out for you before I suggest that you pause the video. So here's the block of wood. We can think about what direction gravity is. So there's a couple of key important points. Gravity is always going to be downwards or towards the center of the Earth. So there's our gravitational force. Now the thing about the normal force is the normal force is always, always, always perpendicular to the surface. So if the surface is going along this slanted angle right here, perpendicular to that means it's going to be moving in this direction here. So this is a normal force, and this is actually enough. Now there may be friction in this case here, there may not. We don't know really enough to say one way or the other. Those two arrows would be sufficient, or if we want to assume that there's some friction, then we can add that arrow there. And another thing about friction is the force of friction is always going to be parallel to the surface, just like the force normal is always going to be perpendicular to the surface. Okay, so pause the video here and please try out 4, 5, 6, 7, 8, and 9, and I'll just go ahead and fill these in after you come back. So pause the video now and give these a try. Okay, so we're back. Hopefully you have paused it. Hopefully you've given it a try. Let's take a look at these ones here. Here's an egg, and it's free falling. So we have the force of gravity, and that is it. We're ignoring air resistance. A plane flies at a constant velocity. Now, I wouldn't worry too much about what you call these forces. You're not training to get your pilot's license, so this is not going to be too important to you, but you can still recognize if it's flying at a constant velocity, that means that the acceleration is zero. And so let's take a look at what forces we have. We are going to have a force of gravity. Now, if it's not moving downwards, that means that there must be an equal and opposite force pushing upwards. And we can call this lift. That's the technical term for this force here. So we have force of gravity and the lift force. We also know that there's propellers that are pushing it forward. And so this is going to be, I'm just going to call it the applied force. You could call it thrust. And we know it's a constant velocity. So if you look at this right here, you should see that there's a bit of a problem. So these two are going to be equal here. But if we have this force that's going to the right and it's at a constant velocity, that means there must be another force going to the left. And this is what we call drag for a plane. Again, don't worry too much about this. The names aren't that important for us. Another thing to keep in mind is that these are going to be balanced. Now, one way that we can indicate that, if we already have these blue ones with one line across, we can have these other ones with two lines across to indicate that FA and FD are also equal. Okay, here we go. Football. Moving upwards towards its peak after being kicked. Well, here's one that may surprise you. This is our free body diagram. So even though something is moving up, if we're ignoring air resistance, force of gravity is the only thing acting on it. So we've seen this before when we talked about acceleration. For something that's moving upwards, we can have a positive velocity at the same time having a negative acceleration. And so in this case here, we know that it must be a negative acceleration because it's a downwards or negative force. So this would be a negative force to indicate that it's downwards. And so this is a perfect example where we can have a positive velocity while still maintaining a negative acceleration. All right, and let's take a look at this one. Force is applied to the right to move a book at a constant velocity. So this is a bit of a tricky question here. So we've got our table surface, and we've got a book that's lying on top, and we're looking at the forces. So again, force of gravity is matched with the normal force, and we also know that I'm applying a force to it. We'll call this Fa, but it's moving at a constant velocity. So there must be something that we're missing here, because if we look at this diagram, our normal force and gravitational force cancel out. I've got some applied force, but it's moving at a constant velocity. So this should tell you that there's some bit of information missing, because if this was the completed drawing, it definitely wouldn't be moving at a constant velocity. There would be a net force to the right, and anytime there's a net force, there would be a net acceleration. So the thing that we must be missing is a force to counteract that, to make sure that we can see that it's not accelerating. And then again, this would be our frictional force. Force is applied to the right to drag an accelerating sled. So here we go. Here's our sled, and again we have Fg, Fn, and these two are balanced. Now we have we have an applied force to the right, and it's accelerating, meaning we're assuming here that it means that it's speeding up. So there may be a frictional force, there may not be. We don't know from the question, but what we do know is that even if there is a frictional force, the applied force is going to be the larger of these two. And last but not least, we have this problem here. A car is coasting to the right and slowing down. So there's our car on the road. Again, this should be quite familiar by now. We've got normal force, gravitational force, and it's coasting to the right. Coasting means that we've turned off the engine. We're not applying any force to the right. So it's moving to the right, but the only force acting on it, the motor is not engaged. This is like putting your car in neutral. It's just moving along. There is no force going to the right, but there will be a frictional force going to the left, which is causing it to slow down. So again, we can see that there's a net force. The force of friction is not balanced by anything, not being canceled out by anything, so that means that it must be slowing down. Okay. What about this? So how do we add these forces together? So they're just like any two vectors. So what that means, if we want to find the net force when two forces are working together, we just simply add them up. So for example, we have this force here plus this force here. Two forces to the right, that's going to equal an overall force that's much larger to the right. What if we have a force to the right and a force to the left? Well, in this case here, I've tried to draw the one going to the right a little bit smaller, so we can add these up and look at this and just recognize that they're canceling out. And we can even do this as vector addition. So if I add this one and then add this one tip to tail, they're kind of drawing on top of each other, but we will see an overall force of being somewhat to the left. So this would be our overall force when we add these two forces together. You might also think of this, it's not wrong to say that you're going to subtract the two. I've heard other teachers refer to them as saying the bigger force wins, and you just subtract the smaller one. But ultimately, we're doing the same thing that we've been doing when we were adding vectors that weren't parallel to each other. We just add them tip to tail. So if I have 5 newtons to the right plus 8 newtons to the left, I would end up with 3 newtons to the left. So however you think about that, that's completely fine. What about if you have many forces acting on an object? So let's say I've got this object here, and there are 3 forces acting on it. Well, the same thing we've always done. We can always just add these forces tip to tail. So in this particular case, let's add the top one first, then a force to the right, and then a smaller force down, and this would tell me my resultant force right there. So we just add all the forces up tip to tail, and we can draw an arrow from the start of the first force to the tip or the finish of the last force. Or, as we've done with other vectors, we can break them into x and y coordinates, and we can look at that. So fx1, fx2, fy1, fy2. There's more than one way to solve these. Tip to tail is one. Breaking them into x and y components is a completely valid method as well. Okay, and I think there's just 2 example questions left. So try to pause the video one more time and we're going to go over these 2 forces, or go over these 2 force problems, but try them out for yourself first. Okay, so hopefully you've had a chance to pause the video. The first thing we're going to do always with these force questions is we're going to draw a free body diagram. So Stan and Kyle are pushing a 75 kilogram sled along a frictionless ice rink. So that means there's no force of friction. Now Stan pushes with 55 newtons. I'm going to call this Fs, and that's going to be 55. And we have Fk, Kyle's force, is going to be 45 newtons. And we also have our other forces, of course. We have Fg and Fm, but these aren't really going to play too much of a role in terms of determining the acceleration because they both cancel out. Okay, so what is our net force going to be? Well, in this case, both of these forces, 55 and 45, these are both positive forces. They're both to the right. So if we add these up together, F net is just the sum of all of the forces. So in this case, that's going to be F Stan plus F Kyle, which is 55 plus 45, which is 100 newtons. And we also know that this 100 newtons, this net force, is equal to the mass times the acceleration, which we have listed as 75. So if we rearrange this equation, we have 100. We're going to divide both sides by 75, and that's going to equal A, and that's going to be 1.3 meters per second squared. So that would be our net acceleration. Now the last example here, again, go back to our free body diagram, and we've got Batmobile here. There is a force of 8.5 times 10 to the 3, so that's 8,500 newtons to the east. We're going to call this right in this case here. The frictional force is 1,500 newtons. And so if the mass is 1250, what's the acceleration? Well, if we were to list out our forces, so what you can do is if you want to, you can list out the forces. So F, I'm going to call this thrust, is going to be 8,500. Force of friction is going to be negative 1,500. So we do need to take count of the direction. And so the F resultant is going to be 7,000 newtons. And it's going to be positive, meaning that it's going to the right. So let's take a look here. So F net, I guess I should have called this F net. F net is equal to mass times the acceleration. In this case, we have 7,000 equals 1,250 times the acceleration. And we're going to divide both sides by 1250. And acceleration is going to equal 5.6 meters per second squared. So that's it for Newton's second law. We're going to go into more examples when I see you again in class. As always, if you have any questions, send me an email or drop by in XBlock. All right, thanks again for coming.